So thank you very much for having me. Um, so this talk is supposed to be sort of a slightly survey overview talk of some of the links between game theory and semi-algebraic geometry. I'll have a quick reminder here at the beginning about what games I'm talking about. Forgiveness from those who find that part elementary. And then I'll introduce semi-algebraic geometry, or at least the parts of it I need. And it's supposed to be a talk that touches on a number of points to give various flavors to. It's not one of those talks where I would be going into detail to the point where everything is understood on everything. So please forgive me if I'm jumping over a bunch of things without taking time for us to become fully acquainted with each, and you can ask me about them later if a particular thing catches your fancy. So I've sacrificed depth for breadth here, in a sense. So, and you can you should, I don't know what your seminar culture is, but you should feel free to interrupt me with questions. I also have the chat window open, but it's easy to miss. So, going back to the 50s, there's this study of subsets of Euclidean spaces that can be defined using polynomial equalities or inequalities. That's what eventually became called semi-algebraic geometry. Of course, there's a much larger algebraic geometry, and then there's this when you allow polynomial inequalities as well, it turns into semi-algebraic, and that it's sort of become an offshoot on its own a bit, even though it has still a strong relationship with regular algebraic geometry. And it turns out that the set of Nash equilibria, which I'll recall shortly, and other related notions such as the Nash equilibrium correspondence, which is a correspondence which assigns to each game its Nash equilibrium and so on, and other related concepts are all examples of semi-algebraic sets, semi-algebraic functions, correspondences, and so on. So for a long time, algebraic techniques and results from semi-algebraic geometry have been used to say things about Nash equilibria and how Nash equilibria change and stability properties and so on. And in the other direction, especially in the past decade or so, there's been a sort of pushback to show that objects that arise in game theory are universal among the corresponding semi-algebraic object. And we're going to see quite a few examples of that in the talk to elaborate what I mean. And along the way, I'm going to touch on some links to complexity of computing or finding Nash equilibria. So that's the potential / quasi-established computer science links. There are a few, some are more established than others, and I'm sure there's a lot still to do there. So the basic message here is sort of Nash equilibria is saying to semi-algebraic sets that anything that they can do, Nash equilibria can do perhaps even better. So to clarify what I mean by games, again, apologies to those from this part is simple. I'm talking about some finite set of players, each with a finite set of actions, and each having, and there being some function, or if you prefer think of it, one function for each player that says, given a profile of actions that are being played, one for each player, this is the resulting payoff. Okay. And what we usually do here to make it interesting is we extend the payoff to mixtures. So each player chooses not a single action, but each player chooses a probability distribution. They simultaneously announce what distribution over their actions they're choosing, and then the resulting payoff is just the expected payoff resulting from that product distribution. So I'll show some examples shortly. Nash equilibrium is then a profile of mixed actions such that each player if he knows the others are going to stick with the mixtures they've announced, they have no incentive to deviate. Okay, so it's a profile Z, that's Z1 for player 1, Z2 for player 2, and so on, such that each player J says my expected payoff now is at least as much as I'll get if I deviate to any of my actions, assuming the others are sticking with the mixtures they've announced. So an elementary observation is that the set of Nash equilibria is a compact subset of whatever space you need the distributions to live in, right? So distribution over at player 1's actions is a subset of R to the A1 and so on, which are defined by these polynomial equalities and inequalities. The first two are saying that each player is playing a kosher probability distribution, right? A non-negative weight on each action with weight summing to 1. And the last line says that for each player and each potential deviation of his, the expected payoff he currently gets, as this is the expectation written out, is at least as much as he would get if he switched to that deviation. Okay, so you're already seeing a link between Nash equilibrium to sets that can be defined using polynomials. So before the example, just Nash's result was that every finite strategic form game of the type I presented possesses at least one Nash equilibrium. And the proof is in sort of almost elementary, sort of simple in retrospect application of Brouwer's theorem, and to find an appropriate better reply map on the profiles of distributions. And when the map returns itself, meaning you have a fixed point, that's a Nash equilibrium. So classical examples are the famous prisoner's dilemma. Say player 1 chooses a row and player 2 chooses a column, and there's a resulting payoff from each profile, which is denoted by the payoff for player 1 and 2 respectively. In here we see the unique equilibrium is the bottom right option, right? Because player 1 gets 1, which is better than 0, so bottom is better than top for him. And similarly, player 2 would prefer right over left because 1 is better than 0 for him. And you can check that's the only equilibrium. Matching pennies. Yes, that's the child game where you both try, one of you is the odd player and one is the even player, and you both put out either 1 or 2 fingers at the same time, and the odd player is trying to mismatch and the even player is trying to match. This is a game where the unique equilibrium is to perfectly mix. Yes, or if you think of a football player trying to score a goal, he wants to perfectly randomize half shooting to the left, half shooting to the right, and if the goalie has no chance of no way of knowing which way is going, he will also go half left, half right. Don't maybe quote me on that because I don't really know anything about football, and it's with great effort that I call it football and not soccer. Coordination game. Here, the players can both coordinate on top left, or they can coordinate on bottom right, or they can play a mixture of putting 1/3 on the first action and 1/3 on the and 2/3 on the second action. That turns out to give each player, it makes each player indifferent between his 2 actions in this case. And that's a particular case of an equilibrium, when everyone's indifferent between their actions, given the other is fixed with what they're doing. There can be more interesting examples. I'll show some later. Here's a nice one where the set of equilibria is topologically a circle. So this game, I'm not going to check it now, but this game has 6 pure equilibria. And in addition, mixing between any 2 consecutive equilibria on the circle is an equilibrium as well. So if player, I have a typo here. This should be bottom left. My apologies about that. So if player 2 is playing left, any mixture between bottom and top together with left will make an equilibrium of the game, and similarly any any of the 6 pure or any mixture between adjacent ones. So topologically, we have a set of equilibria being a circle here. That brings me to our first hint towards universality. This was proved just a few years ago, with a slightly weaker version being proven a few years before that, but it was something of a folk conjecture in game theory. I think everyone believed it, even for many years, even though no one had written a proof. And it basically says that topologically, Nash equilibria can do anything. So every compact simplicial complex, yes, that means a set that you build from simplices and gluing the simplices together on their edges and faces and higher dimension generalization of faces, so on, is homeomorphic to the set of Nash equilibria of some game. Okay, so any compact simplicial complex, I can build some game such that the set of equilibria is topologically the set you've given me. So in one universality notion, topological, anything goes. And this isn't what I'm talking about today, but there's an interesting open question here that I'm trying to get some of my PhD students to work on. What about diffeomorphism? So if I give you a simplicial complex, compact simplicial complex already in Rn somehow, and I want to build a game such that its Nash equilibria are diffeomorphic to this one, formally meaning that a neighborhood of the complex is diffeomorphic to a neighborhood of the equilibrium in a way that the complex goes to equilibria precisely. So unknown even for fairly simple sets, simple lines with kinks and so on. So probably a lot of low-hanging fruit there that should be looked into. Okay, what do I mean by semi-algebraic? So semi-algebraic is a set in Rn that can be defined using a Boolean combination of polynomial equalities and inequalities. So here you have an example. By inequalities, by the way, I mean strict or weak, doesn't matter. This smiley face here, you can see this first inequality defines this larger ellipse, and then these next two elaborate the eyes, and then there's some condition here that takes out the mouth, and ta-da. Okay. So anyway, you can define using ands or negations on polynomial equalities or inequalities. Here's a more artistic one. Unfortunately, I've only seen it online, so I don't have the full inequalities, but I'll trust that it comes out to be something like that. So basic facts, clearly they form this collection of semi-algebraic sets forms an algebra, meaning it's closed under finite unions, finite intersections, and complements. That's immediate. A much deeper theorem with far-reaching consequences, and sort of very non-trivial, is that it's closed under projections. So if I project a semi-algebraic set from Rn to a lower dimension Rk, the result is also semi-algebraic. That goes through something called elimination of quantifiers. So there's even an explicit algorithm that could be shown how to do this. But it's not an exercise like the first line is. And as I've already said, I just said it before using the term polynomial inequalities, but now I can say it's semi-algebraic. The set of Nash equilibria that I just wrote before is compact. That's a easy exercise. Non-empty, that's Nash's theorem. And now, from definition, is also semi-algebraic. So that gives the first couple of easy applications. So first, for example, semi-algebraic sets have finitely many connected components. And as I didn't write it here, but they're also nice enough so that connected is the same as path connected for semi-algebraic sets. There's none of those weird ones where topologically connected is not path connected, or vice versa. Whichever one implies doesn't usually imply the other. So from that, we can immediately deduce that the set of Nash equilibria has finitely many components. In fact, this direction can be taken further, because if you look in the literature, there's a bunch of work on showing how you can bound the number of components of a semi-algebraic set, given that you know the dimension they live in, the number of polynomials, and their degree. So from those 3 bits of information, you can say how many components they have, and therefore, if you know how many players and strategies they have, you can use those bounds to give you an explicit bound on the number of components of Nash equilibria. So that's one first easy application. Again, relies on heavy tools from semi-algebraic geometry, but if you know those, then you can do things pretty easily here. Other nice properties involve using the Tarski-Seidenberg principle, which was what I said about it being closed, these collections being closed under projections. So being closed under projections in terms of logic means that they're closed under the existence quantifier. So earlier from definition, they would have been closed under disjunction, conjunction, and negation. But if they're closed under projection, it means you could also take the existence quantifier over reals, so not over integers, say, but you have to take the projection, which means taking existence quantifier over reals, or if you were doing this more generally, over whatever field you're defining them. And since they're close to complements, that also closes under the for all quantifier as well. So this allows us to show things, for instance, that the closure of a semi-algebraic set is semi-algebraic, right? Because if you had a formula defining a set A, then the set which defines its closure could be built from it using some quantifiers. Yes, so how do you say closure? You mean for every epsilon, it's all the points such that for every epsilon, there's a point in Rn which is in the set and also whose distance is close enough to it, right? So, without verifying it explicitly, from topology 101 that using some sequence of quantifiers here, you can express closure. So therefore, if your original set was defined by a formula with polynomials, so will the closure. Another example that's useful for us, suppose I have a semi-algebraic function. So semi-algebraic function means that its graph is semi-algebraic. A semi-algebraic function of 2 variables, or some subset of 2 variables, where we think of the first as a parameter and the second is something we're trying to optimize over. So lambda may be, say, the price of some goods in the market, a vector of price in the market, and x are those goods, our amounts of those goods, and u is how much we sell the goods for. It would give me the total profit. For each vector of prices, I want to find what the best combination of goods is. So the function that gives me the supremum is a function of lambda. Okay, so the function that for each lambda tells me fix lambda, solve the problem of maximizing u over x, and fix lambda and give me the result. That will also be a semi-algebraic function. That's because to say that some amount v solves the supremum, again, without going into it, you know how to write supremum. It's some formula written with quantifiers over real numbers. So therefore, it's also semi-algebraic. And this, for example, gives us that if I do the same thing, but now it's a function of 2 variables. So what does a function of 2 variables give me? That gives me what's called a zero-sum game. So it's a game where I only need to denote one player's payoff, say player 1, player's 2 payoff is just the negative of that. And for those games, the equilibrium payoff is called the value. It turns out to be well-defined and can be written as a max-min, or what turns out to be equal to the min-max. So maxing over one player's mixtures, minimizing over the other player's mixtures gives you the value, the unique equilibrium payoff of the game. So if I have a family of zero-sum games that depends on some parameter lambda, the function which says what the value is given lambda is also semi-algebraic. Okay. And the further niceness properties that I'll use is semi-algebraic sets have well-defined dimension. So there are a number of equivalent ways of defining it, any reasonable way, such as the highest dimensional sphere you can that you can embed in it using a smooth map is one way of defining it. It rules out weird sets such as the sine 1 over x curve, infinitely many lines here. So this is all the lines of slope n, yes, slope 1, slope 2, slope 2, all of those rule out. Infinitely many stairs can be ruled out. So it imposes a strong tameness on the sets. In fact, there's a whole branch called tame geometry, also called O-minimal geometry, that studies O-minimal categories, which are a generalization of the semi-algebraic sets, which retain a lot of their niceness properties, but allow a little more room than the strict algebraic conditions. It's useful that generic sets are of lower dimension. Once I have a notion of dimension, I can talk about a lower set being generic. I don't have to resort to saying measure 0 or category 0 or other cumbersome analytic notions like that. I can just say generic means of lower dimension. Complement of generic is lower dimension. And usefully, for example, semi-algebraic functions are differentiable except for degenerate sets. They're piecewise, monotonic, all sorts of nice things like that. So I mentioned some easy applications. Let me quickly mention some of the slightly more cunning applications with, again, my apologies, emphasis a bit on breadth and not on depth, just giving a sort of taster of many things. So one really important application comes from this Boolean-Kohlberg result that deals with a class of games called stochastic games. So in stochastic games, without bringing the whole definition, you have essentially a Markov chain that's being controlled by the players. So there's a set of possible states we can be in. Each state is a game in itself with its own payoffs. And in addition to each state and each pair of actions the players play, if we're talking about the two-player zero-sum case as I am here, you get a distribution over the states we can move to tomorrow. Okay, so sometimes these are called Markov games, for example, because it's essentially sort of Markov chain, but just with transitions controlled by the players. Or you think of a two-player Markov decision process. And one of the things that that's nice about these games that Lloyd Shapley already proved when he introduced them, that if you look at the discounted sum, so you put a discount factor, you sum the payoffs over the infinite time horizon, but just you discount them. So the first is multiplied by nothing, and the second by 1 minus lambda. The first is multiplied by lambda, then the second by lambda times 1 minus lambda, then lambda times 1 minus lambda squared, so that the weights sum to 1, but you can sum it all with uniform convergence and so on. You have a well-defined value to this game. That value, I remind you, that's the equilibrium payoff for the zero-sum case. And each player has a stationary optimal strategy. So stationary, I mean they need to condition their action only on the state today, not on what's been done in the past. And if you assume that the state is there's the state space and action spaces are finite, then you can talk about how the value changes as a function of the discount factor. It obeys an equation like this, which it comes from dynamic programming. So this would be a Bellman type equation that says that the value function obeys a sort of fixed point equation, with the value today being some weight between the best payoffs you could get today plus the best payoff you could get to the future. So it's a way of breaking down the problem facing the decision makers today to just do this today and then try to do the best from tomorrow onward. So given that this equation satisfies something like this, we already said the value as a function of lambda would be semi-algebraic. Okay, that's what I said a few slides ago. So I have here a game that depends on the actions, but also on this discount parameter lambda. This will be a semi-algebraic function. Semi-algebraic is a function of lambda, which means that the value of the game as a function of the discount factor is a semi-algebraic function. This, for example, means that it must converge, because remember, semi-algebraic functions are piecewise monotonic, so in some neighborhood of zero, it's monotonic, and it's bounded by a bound on the payoffs in the game, so it has to converge. And in fact, so later papers also use the fact that its convergence is then nice. It's not a wiggly convergence; it's a nice monotonic convergence in some neighborhood of zero. So that this has led to a lot of important work on these games, and it's also raised a couple of challenging open problems. So it was only about a decade ago that it was shown that if the action spaces are not finite, say the action spaces are the unit interval, so still finite state spaces, but now infinite action spaces, you may not get this convergence. So it simply wasn't known, but about a decade ago, someone, Guillaume Vigeral, whose name I'm going to mention here, showed that if you only assume compact action spaces, and then of course everything depends continuously on action, but no other assumption, then you could have V lambda do a sort of sine 1 over x dance as lambda goes to 0. But the payoffs and transitions in that example are not nice. I mean, they're continuous, but they're not nice. So the question is, what happens if the natural question is, what happens if we assume, say, the unit interval as actions, but then we require payoffs and transitions to be themselves semi-algebraic? Then will we get nice convergence? We know that in itself will not make V lambda semi-algebraic. The question is, might it make it belong to some larger but still nice class? And another question is, still keeping everything finite, which functions can V lambda be? So there's a paper from a few years ago which analyzes the single player case, which is just a Markov decision process. And they show that in that case, the value, which is just the optimal solution to the optimization problem that depends on the discount rate, can take on, it can be any function which is a pointwise maximum of finitely many rational functions with some additional condition on the roots of the denominators of the rational functions. I don't remember it exactly, but there's a precise characterization for a single player case. So interesting what happens when you allow two players. Another type of thing you could do with this, again, they really don't want to get stuck on any details, is you can show that for generic games, the set of equilibria is a finite set. So this is one of these things that's been proved quite a number of times in the literature. And you can also prove it using properties of semi-algebraics. That's essentially by using the fact that anything that doesn't happen a lot happens on a set of lower dimension. Formally, that's sort of a semi-algebraic version of Sard's theorem, by saying if you have a continuous semi-algebraic function between two spaces of the same dimension, then generically the inverse of a point is finite. So the graph you should have in mind is something like this. If I have here the projection from this curvy set down to the lower dimension, which is given by the black line, there can be a few points like this one and this one, such that the inverse of the projection is infinite. But generically, like for this black line and this black line and this black line, you only have finitely many points projecting down to it. So you can't get a sort of super wiggly fractal line that makes it so that the set of points above which you have the set of points down here above which you have infinitely many points projecting to it is infinite. Okay, can't get something bad like that. And using that, what they do is they define some wiggly set of this, some manifold, such that what you have here is the space of games, right? The space of games is a Euclidean space, right? It's just however many payoffs you need to specify in the matrix. And they define some manifold over it such that a point here, its first coordinate is the game, and the other coordinates are equilibrium strategies and payoffs. Okay, so all the equilibria of all the games are somehow on this manifold, which of course will be in much higher dimensions, right? This is just in the 2 dimensions I could draw. You'll typically have a many-dimensional space of game, and this manifold of games with their equilibrium will be many dimensions, but the same sort of idea holds. If you project down just to the game, you can only have generically, you can only have finitely many equilibria dragging with it. And a very recent application, I'm not getting many questions. I hope that's the everything is understood to a desired degree silence, not the no one understands anything silence. Although it's possibly the new Zoom silence of everyone is only half paying attention while actually grading or writing exams or something. So this is a recent work of mine where I said, suppose you have some number of players, and you should think of them as having many actions, which are thought of as points in Rn, possibly a continuum, but it could also just be a large set in Rn. And for simplicity, let's normalize all the payoffs to be between 0, 1. And we are looking for epsilon equilibrium. So epsilon equilibria are profiles where each player can only profit up to epsilon by deviating. So that's sort of what you have to do if you only have a discrete set of mixed strategies to look over, right? If you can't expect to look over all mixed strategies with a computer program, say, so you need to look for epsilon equilibria. And what you want to know is how big the supports need to be. In other words, how many strategies you actually need to put positive weight over to get an epsilon equilibria. Okay, it's sort of easy to show that you can, for instance, even if you have a continuum, you can get epsilon equilibria with finite support, right? Just take a fine enough grid, but you actually want to get some bound on how big this may be. And if you had finitely many actions, but say you had 1 billion of them, you might hope for smaller support in your equilibria. So normally you can't say anything else, but Um, but if we know that the payoffs are semi-algebraic, it turns out that we can say more. So if we know they're well, let me state the result in this. So there is some function. It's not important what it is. You can see it doesn't have sort of weird exponential growth or something. It's tame from that point of view, very polynomial, and then some in all the parameters. So it depends on the number of players and the dimension their payoffs live in, the degree of the polynomials defining the payoffs. Sorry, this is the degree and the number of polynomials you need to define the payoffs. Okay. So if you know all those things and you specify an epsilon, I can tell you exactly how big your support needs to be to have equilibrium strategies with support that size. Okay.
Sorry.
Yes.
Do you know how tight this bound is?
Oh, good question. So it is pretty tight in terms of most of the variables, particularly this 1 over epsilon squared, this linearity in M. Not sure about this last logarithmic factor, but that grows a lot smaller. So up to this last logarithmic factor and up to the dependence on the number of players, it's tight. The number of players is an interesting open question. Even in works that don't deal with the semi-algebraic part, we don't know how the number of players affects the support needed. So even two actions, take even two actions. You want epsilon equilibria, so the mixed actions are now anything between 0 and 1. It's unknown if you really need the support size. Sorry, not the support size, because there are two actions. I mean to say, yeah, when they choose mixed equilibria, you want them to choose on a grid, say, not any mixture of 0, 1. You want them to choose weights with multiples of 1 over k in that case. So it's not known if you need k to depend on the number of players at all there. If you want later, I can refer you. There are some papers that show that this problem is equivalent to some other problems, and also, one of these problems that I can say that smart people have thought about it. And the technique, by the way, behind this has a pretty strong computer science relation, in the sense that what you do is you take the data, the number of polynomials and their degrees and so on, and you use it to bound the pseudo dimension of the payoff functions. So pseudo dimension is a generalization for functions of the VC dimension. Yes, the Vapnik-Chernyakhovskis dimension, which is used in machine learning and stuff. So there's that's a notion for complexity of sets. There are several generalizations. I use one for functions. So with those, you bound how complex in terms of pseudo dimension these functions could be. You derive some results for support needed if you can bound this, if you know the pseudo dimension of functions, of the payoff functions, and then plug your bounds in. And the equilibria there are built pretty explicitly by you start with a real equilibria, which you know exists, and you do random sampling, and your random sampling is guaranteed with positive probability. So it's a probabilistic existence proof to sorry, the sun just came out. It distracted my train of thought. That's perils of Glasgow. It's known with positive probability after such and such samplings, what you'll have is an epsilon equilibrium. Okay, so those are some applications. And with the time left, let me talk about what this universality thing I was mentioning about. So when you're talking about two-player games, I'm giving you some examples here of how things get spicy when you go up to at least 3 players. So in bi-matrix games, 2-player games, for example, it's known that if all the payoffs are rational, then you're going to have at least one equilibrium with rational weights, okay, and hence rational payoffs. For 3-player games, this isn't so. So Nash already in his original paper has a generalization of poker with 3 players, rational payoff, probably integer payoffs, I think, unique equilibria with irrational weights. And in fact, for any algebraic number, it's been shown that you can have a 3-player game with rational payoffs and a unique equilibria such that some player gets payoff alpha in that equilibria. And in fact, his result is somewhat stronger than that. He has some hints at complexity of equilibrium sets. He also has this nice example I'll bring here of equilibria, which are exactly a circle. So he defines a 6-player game with rational payoffs, such that the projection to players 1 and 2 is this set. So each player has 2 actions. So the mixtures of each player are the interval. The projection to players 1 and 2 are these equilibria, and for each point on the circle, you get a uniquely defined equilibrium strategies for the other players by these last ones. Interesting ways, I think, not yet studied to generalize his construction. In particular, his construction has one equilibrium, this one, which has some additional stability properties that the others don't have. So there's some questions whether you can always find, even if you have a continuum, must you always find some specific special points that have some stronger equilibrium properties. As it's a little known paper, since Bubelis was not sort of a mainstream game theorist, he was a Russian probabilist who did some game theory that sort of flew under the radar. So other ways that games with more than 2 players differ is that when you have 2-player games, the set of equilibria, sorry, I want to skip this part. Let me jump to here for lack of time. The set of equilibria payoff, so these are payoffs in the plane because there are 2 players, can be shown to be a finite union of rectangles. Okay. And in fact, there's a nice converse from some guys at Tel Aviv that any finite union of rectangles, with sides horizontal to the axes, I mean, is the Nash equilibrium of some bimatrix game. So here's a universality result on the rectangle, these sort of rectangles using only bimatrix games. Now, if you have at least 3 players, how can you limit then? Well, there's another nice result by Guillaume Vigeral, who I mentioned earlier in relation to the stochastic games, which shows that if you have at least 3 players, by the way, it's been in preparation for quite a number of years, but 5 years or so. It's not quite hot off the presses. So for any number of players, at least 3, any compact non-empty semi-algebraic set in Rn is the set of Nash equilibrium payoffs of some game with n players. So there's a sharp discrepancy here when you go from 2 to 3. 2 players, just unions of rectangles like that. 3 players, anything that you think would go. So non-compact, we know from Nash. Non-empty, we know from Nash compact. The easy exercise, semi-algebraic, almost by definition. But other than those properties, all bets are off. Now that concerns the payoffs. There's a result I have, and it turns out the same time Guillaume and someone else, Yannick Voissa, who we're going to have speaking on Zoom soon also, proved independently, and we thought about merging the papers, but mine was for a special edition that had a deadline, so we decided to, and the techniques are totally different anyway. this my result. This result says that if you give me any mixed set of strategy profiles, so now it's not payoffs. I'm moving from payoffs to the actual profiles. If you give me any non-empty compact semi-algebraic set of profiles, I may not in general be able to make it the equilibria of a game with these action spaces, because, for example, it could be that the set I gave you has too many components, for example. Because, as I said, if we know the number of players and how many actions they each have, I can get a bound on the number of components. So if I've, for example, given you too many components, and you already can't hope to get it as an equilibrium with precisely these action spaces. But what I show is that you can add a number of players, binary players, 2 action players, and you can define a game on the larger set of players, such that when you project the equilibria of the new game to the original players, you get exactly the set you began with. Okay, so I can get any compact non-empty semi-algebraic set of profiles, but I might have to add more players and then project back. Okay, so that's a step in the universality direction of I want to get the set exactly. Yes, if I wanted it only topologically, then I have that earlier result that said you can do that. I want to get it exactly. I'm going to have to compromise somehow because I may not be able to do it with just these players and actions. I can do that by adding and projecting. Oh, I'm sorry. I see I missed a question in the chat. Does which thing generalize to cubes? Was someone asking? Was it this thing you were asking about?
Yes, if any union of rectangles results in a Nash equilibrium of a bimetric scheme, does any union of cubes in higher dimensions result in form of Nash equilibrium in higher?
Nash equilibrium pales. Well, Visual's result says, well, yes, but not just cubes. Anything?
Yeah.
Okay. Now, this, it turns out, was not what I was trying to study. It was a byproduct of another result. And then it turns out that this result had connections to the result on proving the complexity of computing Nash equilibria. So, sorry, let me just take my sweatshirt off. Sorry, so I'll state it and give examples, and then I'll tell you what the connection was. So this is the following. I have some semi-algebraic function, continuous semi-algebraic function on a semi-algebraic domain. As I remind you, semi-algebraic function means its graph is semi-algebraic. Then there exists an affine embedding from Rn into the space of, sorry, should that be R? That should be Rm. Sorry, it should be this dimension. So I can embed Rn into the space of games with some number of players, at least this K, okay, at least as many as the image, and then some extra, such that if I want to get exactly the G of the input, that input in A, what I should do is plug that input into T, I get some game, find its Nash equilibria, and then project those onto the first K coordinates. Yes, because a mixed action of a binary player can be thought of as a number between 0 and 1. Yes, that's what I mean here. So any continuous function from a semi-algebraic set into the cube can be represented by you embed well, all of Rm, sorry, as I said, that should be Rm. You embed Rm into the space of games such that on this set A, putting something into the function is the same as putting it into this mapping, finding the game, taking its Nash equilibria, and projecting. Okay. I'm not saying, by the way, that the Nash equilibria of this game are unique, but they all will project on those k coordinates to the value of g. Okay, so that's a more explicit writing. Sorry, for each p in the domain and every Nash equilibria of the game assigned to p, I get exactly that. For those coordinates of z and k, zi is the corresponding output of g. So let me give you some examples of this. So let me start with the identity function. And just for simplicity, allow me to look at it on the open interval, not the closed one. So if you take a game like this, how to understand this game? Well, when Q is exactly half, you have the game matching pennies here. So when Q is half, the off-diagonal entries are -1 and 1. So as Q moves from 0 to 1, you get a perturbation of matching pennies. And it's easy to check that the unique equilibrium of this game for each fixed Q is for each player to put weight Q on his first action and 1 minus Q on his second action. Okay, so in this way, this game sort of simulates the identity function. Okay, that seems kind of useless. What do you do with that? Well, let's see how we can get a game to simulate addition. So let's look at addition. I have to make the domain from 0 to half if I want the output to be between 0 and 1. So let me restrict it that way. Suppose the players, suppose I make 2 players and I make them play the game, which is precisely this H, but instead of Q, I put X plus Y. Okay, so that's indeed a linear embedding of X, Y into the space of games. Okay, I want the embedding to be linear, and that indeed does it. Affine, not linear, affine. And if I replace Q with X plus Y, then of course these players will each be putting weight X plus Y on their first action. Let me make it more interesting. Suppose I want to get multiplication. Or here I put multiplication and addition. So I'm doing it on a domain such that the output will be between 0 and 1, looking at the function x squared plus y squared. And I want to embed linearly into the space of games such that I get this game to play this function. So let me take 6 players. The first 2 will just play h of x, h from the previous slide. So they will each put x on their first action. And yes, I'm aware of the time, finishing shortly. The next 2 players will just play the game h of y. So they'll both, in equilibrium, they'll both place y on their first action. And then I'll have 2 more players, which will play h of some combination that the first 2 players have played. So in equilibrium, if they know that player alpha 1 is playing strategy U, and meaning putting weight U on one action, 1 minus U on the other, and player beta 1 is putting weight U of beta 1 on action 1 and the other, and so on. From their point of view, they're seeing the expected game, which is this. Okay. And because this depends affinely on each other player's actions, this is a kosher definition. I can define H as a function of the pure action profile that the other played and get that when they play mixed, this is still the expected game. Okay, because the dependence in each individual other actions playoff is affine. Okay, so in equilibrium, these first two will be x and these next two will be y. So they'll be facing the expected game h of x squared plus y squared, and therefore they will play the strategy x squared plus y squared. So you can continue in this way to represent any polynomial defined in a bounded set, and then to show that and you could show that the set of functions you can represent this way is closed under compositions using this trick of just plugging, you make some players realize one function and then you plug that into the payoff of other functions. And then you can actually generalize it for all semi-algebraic functions using some trick that I don't want to get into. But it turns out that these gadgets, as they called them, were precisely the tools that were used in the seminal paper of Daskalakis, Goldberg, and Papadimitriou. They did it a little differently, but conceptually, ex post, after I've done my work, it turns out that it's very similar to what they built in their paper on computing Nash equilibrium. So also there, they construct a game with many players, but then they want to show something for three-player games. So they do a direction for 3 players that's actually similar to a direction to something that's mentioned in one of the earlier papers that I mentioned in one of the earlier papers by Boubelis. In fact, they mentioned Boubelis briefly in their paper as well. So the construction there is a little less general because they don't need all semi-algebraic functions. What they do is they account for epsilon equilibria because they're computing complexity of epsilon equilibria. Yes, you can't have complexity of precise equilibria. And if I suspect, and there's a little discussion on the paper, but I suspect that if you do a little complexity analysis on some of the semi-algebraic geometry algorithms that I rely on, I suspect you'll end up getting a similar complexity result to what they showed. In other words, my constructions are also fairly linear in the complexity of the function you've inputted and things like that. So super short summary, semi-algebraic sets and functions are nice, and they have properties that have been used and continue to be used and applied to game theory. And more recently, especially in the past decade, it's been shown by your humble servant and other researchers that Nash equilibria and the Nash equilibrium correspondence show some universality properties among semi-algebraic sets, functions, correspondences. I didn't mention here, but I have a more recent work on semi-algebraic correspondences and fixed point correspondences and things like that, and their relation to the Nash equilibrium correspondence. And there are some natural relations to the complexity of the structure of Nash equilibria, of computing Nash equilibria, some of which have been explored and some of which have yet to be fully explored. And if you're interested, probably the best place to start reading is if you look in this textbook, or this edited book, Stochastic Games and Applications. Abram Neyman was my supervisor, one of the editors. There's a really nice chapter there. It does bring in stochastic games, but also simpler games, and it's a really gentle introduction to semi-algebraic geometry and its relation to game theory. So I will end there and open it up for questions.